What is load flow analysis? Load flow analysis, also known as power flow analysis, is a fundamental technique used in power system engineering to determine the steady-state operating conditions of an electrical power network. It involves calculating the voltage magnitude, phase angle, and power flows at various buses, nodes, in the system under different load conditions. The load flow analysis is essential for assessing the performance and reliability of a power system, as it helps identify potential problems such as voltage instability, overloading of equipment, and reactive power issues. It is typically performed during the planning, design, and operation stages of a power system. The analysis involves solving a set of nonlinear algebraic equations known as the power flow equations. These equations are based on Kirchhoff's laws and the principles of electrical power transfer. The variables in the equations include voltage magnitudes, voltage angles, and real and reactive power at each bus. The load flow analysis considers various components and parameters of the power system, including generators, transformers, transmission lines, distribution feeders, loads, and shunt devices such as capacitors and reactors. By iteratively solving the power flow equations, the analysis calculates the voltages, currents, and power flows throughout the system. The results of a load flow analysis provide valuable information about the system's voltage profiles, power losses, voltage stability margins, and reactive power requirements. This information helps power system engineers make informed decisions regarding system planning, expansion, and operation, such as determining optimal generator dispatch, identifying voltage control devices, and evaluating the impact of new loads or generation sources on the system. Load flow analysis software tools are commonly used in power system analysis, as they automate the iterative calculations required to solve the power flow equations. These tools provide graphical representations of the network, voltage profiles, and power flows, facilitating system visualization and analysis. Bus classification. In power system analysis, buses are classified based on their characteristics and functions within the network. The most common classifications of buses are: 1. Slack bus, reference bus or swing bus. The slack bus is the reference point for the system's voltage and phase angle. It represents the largest generator or the external power system to which the network is connected. The slack bus has a specified voltage magnitude and angle and is used to balance the system's power generation and consumption. 2. PQ bus, load bus or constant power bus. PQ buses represent loads or consumer loads in the power system. These buses have fixed values of active, real, power, P, and reactive power, Q, and are used to model the demand in the system. PQ buses typically represent residential, commercial, and industrial loads. 3. PV bus, generator bus or constant voltage bus. PV buses represent generators or distributed generation units connected to the power system. These buses have fixed values of voltage magnitude, V, and active power, P. The reactive power, Q, is allowed to vary based on system conditions. PV buses are used to model generators and their associated voltage control devices such as automatic voltage regulators, AVRs. 4. Slack PQ bus, slack load bus. In some cases, a bus can function as both a slack bus and a PQ bus. This occurs when a bus is connected to an external power system and also has a local load connected to it. In such cases, the bus acts as a slack bus for the interconnected system and a PQ bus for the local load. 5. Slack PV bus, slack generator bus. Similarly, a bus can act as both a slack bus and a PV bus. This occurs when a bus represents a generator connected to an external power system. The bus acts as a slack bus for the interconnected system and a PV bus for the local generator. By classifying buses in a power system, engineers can analyze and solve the load flow equations more efficiently. The classification allows for the proper modeling of various components, such as generators, loads, and voltage control devices, enabling accurate analysis of power flows, voltage profiles, and system stability. Sure. Here's a